Okay, so in this video we're going to cover how to integrate the convolution to the circuit into an AXI4 interface, actually into the AXI4-Full interface. Again, all we're doing here is following the tutorial number 4. All these steps that I'm going to mention are already explained in the tutorial number 4. Okay, and you have to go, of course, to the AXI-Full convolution to the example. The files that you need to download, they are right here. If you go to the tutorial website, you can download these files. What is the hierarchy of these files? Right here. So I already explained this for a previous example, but remember, this is the top file of the AXI4-Full Peripheral. Okay, it's just a wrapper file, by the way. What about this? This is the file that implements the AXI interface. Essentially, it just deals with generating this signal, dealing with these signals and generating, for example, this signal here, AR ready or AW ready, and so on. Okay, so that file does do it for you, so you don't have to do it on your own. These two, like I said, they are provided by Vivado. They are a template, but just to be careful, we have edited this file and made some significant modifications. The most important one is we remove the 64-byte memory example. So by default, in the template, there is a 64-byte memory example. We removed it because we plan to place the FIFOs. Okay, and not only that, I made a slight modification to the generation of the signal. Let me see, what is the signal here? R valid. Essentially, you can see from here, if the output FIFO is empty, right, this signal becomes 1, and therefore the output of this flip-flop will become 0. So essentially, if there is no data on the output FIFO, and the master, which is the microprocessor, wants to read data, well, the master will keep waiting until there is data on the O5. Okay. Okay, after that, we integrate now the FIFOs, and this is done actually right here in these two files. This file here, again, is a wrapper, and this doesn't work anymore. Only the FIFO based approach is available. But it's just a wrapper, by the way, that instantiates the following file, my AXI5, which is a real file that we need. This file, of course, includes the FIFOs and the FSM at AXI 8 clock, which is a blue state machine, right? This one right here. Okay, and what else? Well, like I said before, after this file has to contain as a component this another file here, which is a circuit that you need to build, right? Of course, I had already built it. That signal includes what? Sorry, this circuit includes what? The FSM, the red FSM, the glue logic, I will explain what that is in a moment, and the parameter setting. Let me mention what this is. So essentially, right here, if I do this, all of this, including this, Okay, so that part, that is what we call the mycom2 underscore ip.vht. Okay, essentially, as it says here, it implements the state machine, the red state machine, plus some glue logic, right? Plus the parameter setting of the convolution kernel. Okay, and of course you have the convolution itself. That's your circuit, right? The top file, and of course there are a bunch of files underneath it. Let's take a look. This is your file. I mean, your design. Looks kind of weird, right? But it doesn't matter because this is your design. Okay, you can design that however you want to, of course. Just make sure that there is an input-output mechanism, right? Like there is an enable, a valid, or a start, and a done, and that kind of stuff. Now, on top of that, we are going to build this IP, which is essentially what? The convolution kernel that you had, and this extra, circuitry, which we call it glue logic, right? That connects the inputs and outputs to the FIFOs. So this circuit here has what? The input coming from the FIFO and the output going to the FIFO. And of course, it also includes some control signals from the FIFOs. Okay, just as you can see in the picture, right? IRDN, so or I read enable. It also reads, I guess, output full. It also writes output write enable, and so on. Okay, so this file, of course, includes my component, and then it includes a bunch of other stuff. But the most important part is this one here. This state machine that you see here, that is the red state machine right here. Okay, and then remember this. Remember, those of you who remember, for the convolution 2D, this state machine is divided into two state machines, right? Let me see if I can, before you forget, let me see if I can find that for you, so that this part is clear, because otherwise this might look a bit confusing. So, if we go to the convolution block, right here, right, we have the red state machine, or at least that's how we prefer to call it. But we made a decision that if this circuit is pipelined, we want the input to be written, at the same time we are reading the output. Because of that, this machine has to be partitioned into two state machines, and these are the two that you see here, two of them, and they work at the same time, right, simultaneously. Because of that, you see here two state machines, okay? One that controls the input side, and another that controls the output side of things, okay? And then we have here, you see, your block, to which I am actually specifying the parameters. Like I said, in this block is where you specify the parameters of this circuit, okay? And in this case, here are the parameters that should be, I think, defined right here, right? All the parameters of the circuit, okay? Okay, and I think that is it. Just keep in mind that what I'm suggesting here, the division of the files, the partition of the components, in these files or across these files, is what I suggest. Okay, it is by no means mandatory. You can, for all I know, have include all of that right into AXI4. You can edit this block AXI4 and include the whole thing inside that file. Okay, that is okay too, but I prefer a more a modular approach, right, where you do it step by step. I think it looks better. Anyway, so that's what I wanted to tell you, and now, well, we're going to just follow the tutorial. Okay, the tutorial, I mean, there's nothing new. This block here has the input interface has 2 registers, such that, remember, we have 72 bits. We have to load, I think, 72 bits, right? Here we load 64, and then the remaining 8 are taken directly from the 5. And then we build the 72 bits right there to fit. The output is 20 bits, so we don't need to do anything except padding with zeros, okay, to get to 32 bits. It's not a big deal, okay? So let's do that then. Let's start. And again, like I said, this process is very mechanical. I explained this a while ago. What is the design flow? You create your circuit, like for example, your pipeline convolution kernel, and then you add the interface circuit to it to create a peripheral. Ideally, you should do this in your own Vivado project, and of course you have to simulate. To simulate, by the way, I have included here a test bench. And I think you've seen a similar example in the test bench of the Pixel processor, right? It looks very similar, right? Except for the name here is different, that's all. The name here is different. The name here is different. The IOs are the same, by the way, because those are the IOs of the AXI interface anyway. And we have, of course, the procedures here to write data and to read data. How do you test this block? Well, it is, by the way, specified in the tutorial, right? We write 3 words of 32 bits and we retrieve 1 word of 1 bit. That's how this works. So here, for example, we have the 3 words, right? And then we execute this command that will fit these 3 words, right there. And then we read 1 word only. And then what? Then we do the second set of 3 words, and then we read 1 word. By the way, this is the same approach we will use when when we test the software code. The software code works the same way, by the way. Okay, so simulating this, by the way, is very, very important. Okay, this I would recommend you, if you have a circuit, you better simulate it. Okay. Okay, now let's go ahead. So I am going to create a new file here. I'm sorry, a new folder, my AXI4-Full COM2. Okay. The name of my peripheral is going to be my COM2-Full. Why? Well, I have made the decision to keep it that way, right? Here, my COM2-Full. You could have, by the way, used any name that you like. So your design, the whole thing. Oops, a moment here. The whole design is called my COM2-Full. But at least that's how I have decided to call it. Okay? To the entire AXI peripheral. Okay. So having said that, we have created this. And now we're gonna create a new project, right? This is supposed to be very easy. Right? You have to just provide the right name. My AXI4-Full COM2. There you go. My AXI4-Full COM2, and then we don't do anything except selecting the particular board that we plan to use, which is, well, whatever you have, right? I have, in this case, the ZYBO Z7, and then I finish. So what I'm gonna do, because I already have my design, right? I am gonna create my IP, right? Which means I'm gonna build my peripheral in Vivado, so I can just drag it and drop it. But in order to do that, I have to create that in Vivado, of course. And doing that means it's just copying all these files, I guess, minus the test bench, and of course you don't use the C file there at all. You copy all these files, right? So you can use them. So now we have this, and we have to create, of course, the IP, right? And the IP, as I said, has to be named my COM2. Like I said, you could have picked any name that you like, but because I have chosen this name here, right, to make it easy for me, I have to use the same name. If you choose a different name, it will create different templates with different names, and now you will be forced to modify these two names here, and also the inside, the code itself, which is a bit messier to do. Okay, my COM2 full. This is not a light interface, but a full interface, right? Here we go, and then we go here, and a new Vivado project will open up. Let's give it a moment. Okay, here we go. So here, of course, it's taking a little while. It already created the two files that constitute the template, right? But we need to replace those files because we have made significant additions to that. So what are we going to do? I am going to grab these files, copy, right? And I'm going to paste it in the repository. I think it's my COM2 full, yep, HDL. You see these two? I'm gonna copy not only those two, but the other one. Of course, I have to replace them, right? And there you go. Okay. And now I am going to add new sources. You have to, of course, scroll carefully to where you are supposed to be at. COM2 full, HDL, and then here and here, minus these two. Like I said, in Vivado 2019.1, this is open by default. Sorry, check by default. I prefer to uncheck it so that a new source directory is not created. Right? To me, the simpler the better. But if you check it, it's not a big deal to be fair. And here we go. That is it. Now we have it ready. Just give it a little bit for this hierarchy to update. So you have here now all the files that you need. So now what do we do? Just in case we want to synthesize, in case something weird happened. Okay. And after this, we're gonna package our component, and then we're gonna, in a different Vivado project, we're gonna integrate the hardware, which is this component, and the PS, right? The microprocessor system. Let's give it a little bit. It's gonna take a little bit of time. Okay. Again, this structure here is what I suggest, okay? And if all of these steps that I'm mentioning here you don't remember later, of course you can always look back into this video, but I have updated the notes, and I think if you go to this page number 19, I think I detail the general procedure, right? I hope this helps a little bit, okay, with what you're doing. Always, it is important to simulate. If we have time, I will show you how the simulation is performed for your peripheral, only your peripheral. Okay, so I think this thing is done already. Oh, it's still taking a little bit. Just give it a little bit more of time. Okay, it is completed now, and then we close this, and then we go to the package, right? Remember, because we have added new files, this portion, the file groups, needs updating. It means merge changes from file groups wizard. That's just a fancy name to, you know what? update this peripheral with the new file that you created. So you do that. Okay, so this will create like a package such that you can just drag and drop, in your design. You drag and drop this component in your design. Okay, and now you're gonna go back to the previous project, and now you can create a new hardware-software system. Okay, and I'm sure you know these steps already. You've done it a lot. It's just click here, click there. Okay, so what are we gonna do? First thing, the PS, right? The processing system. The second thing is your circuit, right? And then you know what to do. You run block automation such that the PS has a particular IOs, and then you run the connection automation in order to connect the PS with your peripheral using the AXI interfacing. Okay. Always, I say to validate your design in case you made a weird connection. That's not very important right now, to be fair, because all the connections were made automatically. Then you go to sources, you go to this block, and then you create a VHDL wrapper file. Just a description in VHDL of the entire architecture. Okay. Okay, let's give it a little bit of time. Oops. Takes longer than expected. There you go. So now, since we're confident this is going to work, because this has been simulated already, right? We're going to just go to generate bitstream. It's going to take a little while, okay? Remember, because this component doesn't have text files, right? We won't run into the same issue that we run when we try to implement the pixel processor. This is a much simpler circuit to build on Vivado. Okay. Okay. Well, let's give it a little time. Okay. So now it finished, and once the bitstream is generated, well, you know what you have to do, right? The first thing is to export the hardware, and remember, you only have to do this once. Okay? So next time you open Vivado, you open this project, all you have to do is just launch SDK. Okay? And when we launch SDK, as I said to you in the previous example, you need to create a test project, right? And then the drivers for your peripheral will be generated. The drivers have the following name. If the peripheral is my com2full, the driver is my com2full.h. Okay? And again, what are the name of the functions? Are like this: com2, what I think is write memory. That's how you write onto a specific memory space. Sorry, memory address of your peripheral, and then my also there is my com2 read memory. Okay. Those are the two functions that you need to interface with your peripheral. So now we're gonna go here, right? What is the next step? Well, we go file, and then we do new application project, and I don't know, com2 test, for example, and then an empty application, and then all the drivers will be generated, the whole thing. So what I'm going to do, of course, is I already have the C file, right? So what I'm going to do, I'm going to just copy and paste. In your case, if you're building a new peripheral and you want to test it, I think you can use, for example, this file, right? And you can edit it, you know, such that you interface with your peripheral. Okay, so I'm going to copy this into the SDK folder. It should be here, and come to test, and we paste it here. There you go. And now what I have to do is to refresh. Okay, let it refresh, and again, let me show you. The BSP is called the board support package. It is essentially a bunch of drivers. As you can see here, you have a driver, for example, for every peripheral in the PS and in the PL as well, like in your block. And in your block, you have the following. Like I said, it's just my COM2-Full. Write memory, you provide the address and the data. What is the address, by the way, if you don't remember? Well, just a moment. The address in this particular case doesn't matter. Any of the 16 addresses will work the same, because we are not decoding the address in this FIFO based example. So you write on any address, it will write on the FIFO regardless. Okay, that happens when you write or when you read. Okay, and again, I think these are just masking functions for the real function, the real low-level function, XIL out 32 and XIL in 32. If you use these two, believe me, that's all that you need to use. Okay. Well, of course, you gotta be careful with this function, because you gotta make sure that you read or write on the address that belongs to the to your block, right? If you write on a different address, right, your software application might not work at all. Okay. 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 So now let's take a look at this. So it is gonna take a while for the this to compile. It is compiling everything, and again, for some reason in the Windows 10 computer, it takes a large time to compile all of that. Let's give it a little bit of time. Okay. Okay, so finally this completed, and now we can open this file. And like I mentioned before, for your if you have your particular peripheral, or you are welcome to use this file as a template, right? And you might need to modify it there, right? Instead of my COM2-Full, whatever, say my example, that will be the different name. Here, the base address actually is provided as a parameter into your circuit. Okay, so here the main difference will be that it will have to be something like this, right? My example. Okay. For example, okay. So the what is it? The base address is specified in the right here, 7AA00000. For example, it can be anywhere, by the way, and it's provided here in this constant that I think exists in this file, by the way, if you look at it, if you're curious about it. Okay, but if you use a different peripheral, of course, you need to change this, but it will be like this. And the same with the functions, right? You use my example full instead. Okay, so you can just, I guess, edit this template for your own needs. So how does this work? Well, as the tutorial says, we write 3 32-bit words and we retrieve 1 32-bit word. And then this is the second step, right? We write the next 3 32-bit words, and then we retrieve 1 32-bit word. And that's what we do right here. Okay. By the way, this is the same thing we did in the test bench, if you remember. Okay? And then we read. Okay. Now remember, we write and read. We write and read. But nobody says you have to do it that way. You can also just write these three, and then write these three, and then read these two. Okay, you can write 6 words and then retrieve 2 words. Why is that possible? Because we have this FIFO, right, that store the data. Of course, there is a limit up to 512 words, of course. Okay, so now let's test this out. So what I'm gonna do, I'm gonna turn on my ZYBO, and then I am going to program the FPGA. Also, when you are updating your C file, my recommendation for you is to always uncheck this build automatically, because otherwise, every time you save your file, it will compile your code. I mean, that might take a little while, so it's better to just build it when you need it. Okay. So now that we have programmed the FPGA, now we're gonna check the terminal, right? We add the port, I think it's COM10, and there you go. And then we go here, and we're gonna run this. And let's see if this works. So a moment here, I think it needs to be saved before it goes. Okay. Here we go then. Here we go. Okay, so now it is completed. Okay, as you can see here. For the first set, this is the result 0002B82. For the second set is 00001A8FF, which happens to match these two. Okay, so this thing works, as you can see here. Okay, so let me close this, and I think with this thing we're essentially done with this video. But I want to show you something as a bonus, because you might need this anyway. I have created a folder here, a project, a hardware-only project with a peripheral. Only the peripheral, which is what you should do, by the way, because you want to simulate your peripheral. So this is very important. You have a Vivado project only for this peripheral. Okay, and you simulate it before you even do the what? Before you create the AXI peripheral in Vivado, right? Before you do what we just did right now. Okay, so I have done that, and I have run the test bench. The test bench, as I explained to you, and this is the example, works in a similar manner. There you go. Works in a similar manner as the software code, by the way. It writes 3 data, and then it reads 1 word, and then it writes 3 32-bit words, and then it reads 1 word. The same thing. Okay. So you have to do this in your code in order to verify that it is working, because believe me, once you are in SDK and if something doesn't work, how are you gonna find out where the error is at? Okay, and you can use again this template, right? The only thing you need to change is what? The name, probably, of the test bench. Also, for sure, you need to change the name of your component, but look, the IOs will remain the same, by the way. Nothing will change. And you will use the same procedure, which is the write data, and also the one to read data. After that, what else do you change? Well, of course, the name of the component under test, just this one. Everything else remains the same. And then, of course, the way you fit data. You might fit data, I don't know, 3 words, and then you read 1 word, or you might fit more data, right? 2 words or 5 words, and you might retrieve more data, 1, 2, 4 words. I mean, however you think about it. Okay. So here, for example, if we have these 3 data, 3 words, we have to specify that by here. This is the length. 2 in this case means 3, by the way. Okay. And when you read data, if you're only reading 1 word here, 0 means we are reading only 1 word. Okay. So now when you test this, when you simulate that, you will find this. It's kind of messy because you have all the signals. You have to kind of classify the signals, right? Order them. This is the AW, is the write address channel. This is the data. Look how the data is being written here. Oops. So you can verify that your data is being written here and here and here. But the most important part, of course, is the read data channel. The read data channel, you will see here that at this moment, when there is valid, when this is valid, you see 000 2B82, right? Which is what we expected, right? And the same for the other 0001 8FF for the second part. Okay, when we write the second part. So this might be a bit messy, but you have to, of course, organize this, by channels. Okay, usually what I do is maybe give me a few minutes here. I insert a divider and I say, oh, I'm gonna get the divider for the read data channel, and then I add there all the signals associated with the read data channel. And I think that should be all, right? R. So this is all the read data channel. You have the valid, the ready to, right here. The valid on the ready, and then the response. This is not so important, but what is important one is the data itself. Okay. So this is the valid and the ready, and this is the signal that tells that it is the last. So at this moment, when these three are 1, that's when it latches data. You have to refer, of course, to the timing diagrams, of course, of the AXI interface, the nodes unit 5. Okay. So this, by the way, is an important exercise for you to complete. Okay. So it will tell you a lot of what's going on in your circuit. Okay. But anyway, thank you so much.